Hi, welcome to Spectroscopy with Pasco. In this short video, I'm going to present how to measure and to investigate emission and absorption spectrum. And here we have an example of the hydrogen emission lines. Start the capstone Pasco software, select graph and select along the x-axis the angle, and along the y-axis should be light intensity. And start recording once you have very clear, sharp spectral lines. So once you start recording, and you should move the light sensor from the threaded post, which is underneath the light sensor, very slowly, such that you are going to scan the spectrum, the first line spectrum on the left, the central fringe, and the line spectrum on the right. And in the video provided, you can see how I move the light sensor from the threaded post. Also on the right side, there is a snapshot of the Excel. I did some calculation in Excel. You can use your calculator to do that. And you can change, you can expand the graph. So you can observe these emission lines, all the peaks, peak for the first red line, the green line, so on and so forth. And you can use the annotation tool to label them. And you can either write what line correspond to each peak, or you can label them 1, 2, 3 like I did. And we are going to measure the angle delta theta between two identical lines, one on the left and one on the right. Let's say the red line on the left and the first red line on the right. And we're going to measure that angle delta theta. Now it is also another option will be to measure the angle from the center of the central line to the location of the first peak or the location of the second peak, and that's going to give us the angle theta, which is in our case corresponds to delta theta over 2. Now let's see what equation we need to use in order to calculate the wavelength corresponding to each line in the line spectrum. As I mentioned earlier, theta used in the calculation is going to be half of delta theta, and this angle theta is going to be in radians. We need to make some adjustments on this equation, and in a little bit I'm going to show you what each quantity means. What is the meaning of each quantity? M is the order of the maximum, and M in our case for the first line spectrum is 1. The constant N is specific for the diffraction grating use, and we need actually D, which is 1 over N. And when we do the calculation, sine theta needs to be corrected for the ratio between the radius of the degree plate and the radius of the small post. So the actual angle that we use in the calculation is going to be the angle theta divided by 60. So in the Excel folder on the right side, I did a calculation for sine of theta in radians using the actual angle with that divided by 60. And in order to measure the angle delta theta, we have to use the built-in analysis tools, and we have to turn on the coordinate tools and drop it in top of the peak and turn on the delta tool and measure the angle. So here we go. This is the first angle delta theta measured between the first two red lines, one on the left and one on the right. And the wavelength lambda shown in the Excel file calculates the wavelength in nanometers. And you can calculate lambda using the angle theta either in degree or radians. Now make sure you make the conversion from radians to degree, or your calculator is on the right setting. So we're going to continue to measure delta theta for each line spectrum. finish all the measurements for delta theta and do the calculation for lambda. At the end, you should have 5 values for lambda corresponding to those 5 lines in the line spectrum. So the next step is going to compare the values we found for lambda with the accepted known wavelengths from NIST. And there we go. This is the last angle, delta theta. I mentioned earlier that the spectrum is bright on one side and not quite bright on the other side of the slit. And you can observe that in the light intensity relative to the central fringe. So the last delta theta is 31.369 radians. Again, divide this angle by 2 and make the correction, divide by 60 and calculate the wavelength. Okay, so looking at the National Institute of Standard and Technology, we can compare and we can do some error analysis. So now we're going to look at the absorption spectrum of the hydrogen. So we are going to place a cuvette filled with green food colorant. Make sure the food colorant is diluted such that the light is still transmitted, the light goes through, it's not scattered. And we are going to do again a measurement of the spectrum, the absorption spectrum now. And you have to move again the light sensor slowly as you go across the lines. The light sensor has 3 settings: the candle, light bulb, and the sun. So for this specific experiment, we are going to select the candle setting. So instead of the cuvette with the food colorant, you can choose to place a leaf in front of the light sensor and to measure the absorption spectra. Now, don't forget about the grounding lead. That is going to eliminate some of the electrical noise. Also, please be aware that this experiment should be performed in the dark. Any light is going to give some additional optical noise in your light intensity measurements. While you are recording the data for the absorption spectrum, push on the threaded post under the light sensor to slowly and continuously scan the spectrum in one direction. Scan all the way through the first order spectral pattern on one side of the central ray, through the central ray itself, and all the way through the first order spectral pattern on the other side of the central ray. Once you are finished, stop recording the data. And the second step would be to compare the emission spectra for the hydrogen with the absorption spectra for the hydrogen after the light from the hydrogen is passing through the food coloring. So you can use the graph display to compare the plot of light intensity versus actual angular position for the first run to the plot of light intensity versus actual angular position for the second run, when you have cuvette with food coloring and the hydrogen light. So you can use the built-in analysis tool to find the angle of the first gap or the dark line in the absorption spectrum of the liquid sample. You can find again the corresponding angle like we did before, and we can calculate the wavelength. We are gonna let this for you guys to do it as a homework. We only compare in this video the two spectra, one for the emission lines and the second one for the absorption spectra.